Alright, so question 2 of the tutorial says we're looking at naphthalene, which melts at 82.2 degrees Celsius. Of course, that's it. That's its natural melting point. And then it says the vapor pressure of the liquid is the vapor pressure of the liquid is 1.3 kilopascals at 85.8 degrees Celsius and 5.3 kilopascals at 119.3 degrees Celsius. Right. So then we're asked to use the Clausius-Capeyron equation first to calculate the enthalpy of vaporization, the normal boiling point, and the entropy of vaporization. So we're given two sets of vapor pressure and temperature data, and also calculate a bunch of things. So let's just start off by writing the Clausius-Capeyron equation. So we just have that for reference. So of course that's ln P2 over P1 equals to minus the vaporization of enthalpy over R 1 over T2 minus 1 over T1. Right. And in A, if we want to calculate the vaporization enthalpy, we can rewrite this by multiplying the R to that side, or actually multiplying this entire part too. So the R to that side, and then dividing by this fraction on the right hand side. So minus R to that side. So we go here minus R ln of P2 over P1 divided by 1 over T2 minus 1 over T1, which is equal to the vaporization enthalpy. Or we can write it as in like a just a different way of writing it would be minus R ln P2 over P1, and then just my favorite notation is T2 minus 1 over T1, and then we say to the power minus 1 there. Okay, so then we just have to plug in our values. So we have a minus 8.3145 joule per Kelvin per mole. Right. Our ln values, so we just use the values that we're given. So let's make what choices shall we make? So let's say we make 5.3 on top, so we make 5.3 kilopascal kPa on top, then 1.3 at the bottom. We just need to ensure that we keep the temperatures aligned. So if 5.3 goes on top, then that's 2, then 119 goes with that. Right, so then that means, okay, so 119 goes in there, so that goes 1 over, then 119 is 392.5 Kelvin point, minus 1 over, and then 85.8 Kelvin is 359.0 Kelvin. Right, to the power minus 1. Of course, you can take the minus in there, then this would just flip. You can really do these things whatever you'd like. You can take the minus into the ln as well, and then just flip the ln. You can do this in a range of ways. And then this should give you a value of 4.9 times 91 times 10 to the power 4 joule per mole, which of course is 4, so we have 2 Yes, two significant figures, so it's 4.9 kilojoule per mole. Okay, so that's our enthalpy, our vaporization enthalpy. Okay, so then the B part asks us to calculate the normal boiling point. So what does the normal boiling point mean? So of course when we ask for the normal boiling point, the normal melting point, the normal vaporization, or whatever that says, normal means at standard conditions. So it means at a vapor pressure, so a vapor pressure of 101.3 kilopascal, or then, you know, the 1.01 whatever 3325 Pascal, whatever you want to use, but we can use kilopascal because we're going to use one of the other sets that we already have been given to calculate that. Okay, and now as we saw in the previous example, or in the previous tutorial question, we can do nearly about anything we want. You can either plug into the Clausius-Clapeyron equation, you can calculate step by step, you can calculate the temperature, or you can rewrite the Clausius-Clapeyron equation and isolate one of the temperatures and calculate it from there. So starting with it again in the form like this, P1 equals to minus vaporization enthalpy over R 1 over T2 minus 1 over T1. Okay, let's say we make T1, so we make the ones, so we want to calculate T1. Okay, that's what we want to do. So in other words, then we take this over, so then minus R ln of P2 over P1 over the vaporization enthalpy will be equal to 1 over T2 minus 1 over T1. So then we're going to take this, T1 is going to go over to this side, and this is going to go over to this side, so then the minuses swap. So then we have 1 over T1 is equal to 1 over T2 plus R ln P2 over P1 over the vaporization enthalpy. Okay. And then of course that just means that T1 is equal to the inverse of this. Alright, so T2, so let's, you can pick any of the other two data sets that you want to pick, but I'm going to pick the 119 degrees Celsius one. So then it is 190, so the 119 degrees Celsius is the 392.5 Kelvin plus then 8.3145 joule per Kelvin per mole divided by the enthalpy. So we use the value times 10 to the power 3 joule per mole, of course, and then this is times by ln of, so now P2 needs to be then 5.3 kilopascal, right? It is 5.3, yeah, 5.3 kilopascal is at 119, and then the other one is so we're at the normal boiling point, the vapor pressure is going to be 101.3 kilopascal. Right, that all is the inverse, so that should give us a value of 2.047 times 10 to the minus 3 minus 1. This is per Kelvin, of course, and then eventually approximately gives us a value of 488 Kelvin. Actually, it is two significant figures, so it's 490 Kelvin. Yeah, right, so 490 Kelvin is what we end up with. Right. I just realized this is actually 49 kilojoules. Just out of the corner of my eye. This is 49 kilojoules. Did I write this thing correctly? This is actually to the power 4. You can see it's very late in the evening. But anyway, the calculation is still correct. That I just copied it incorrectly from where I was writing. Okay, so that is that is it, and it's actually quite close to the literature value, because this is around about 215 degrees Celsius, and the accepted literature value is 218 degrees Celsius. So where the boiling temperature at atmospheric pressure is 218 degrees Celsius. So our estimation here is not too bad. Okay. So then finally we look at C. We're asked to calculate the entropy of vaporization at the boiling point. So basically all that we're left to do here is we need to recall something from theme 3, and that is that the transition entropy is equal to the transition enthalpy divided by the transition temperature. Right. Maybe you remember some equation like that. So in other words, then the entropy of vaporization will be equal to the enthalpy of vaporization, which we calculated, divided by the temperature of vaporization. Other words known as the boiling point temperature. So that's why we calculated it. So this is then equal to 4.91 times 10 to the power 4 joule per mole divided by 488-ish Kelvin, which then gives us plus 101 joule per Kelvin per mole. Yeah, which of course is positive. Interesting that it is positive. Entropy of vaporization. So in other words, not interesting that it is positive, because I mean we're going from liquid to gas, so in other words indicates increase in disorder, so we expect it to be positive, so not really a shock. Quite large. Interesting that it is quite large, so it indicates quite an excessive increase in the disorder from the liquid to the gas. but it could also be because of the high boiling point, high-ish boiling point. The boiling point is quite high at 218 with a 215 degrees Celsius, so it could be because of that. So yeah, that is essentially it for question 2. Of course, you could have calculated this middle one or any one of these really by just plugging in the values and going step by step. But you know, I like to do the algebra route, so yeah. And I do apologize for the little mistake with the vaporization enthalpy. So just, it will be correct in the notes, I promise. So just check, but it shouldn't be, yeah. I picked it up before finishing. Yeah, anyway, so that is question 2.